flash of heat, a shock of water, and raw iron becomes hardened steel. Before this metal can drive a heavy truck, it must endure extreme thermal stress. Here is how it happened. Every one of these heavy-duty truck axles begins life as rusted marine chain. Reclaiming ship anchors requires brutal disassembly. The oxy-acetylene torch reaches temperatures exceeding 3,000 degrees Celsius. This intense heat doesn't just melt the iron. It rapidly oxidizes it, blasting away decades of rust and marine degradation. The cutting flame severs the thick links, breaking the massive chains into manageable chunks. Working with heavy salvage is a battle against sheer weight and structural fatigue. The operators coordinate to position the heavy links, utilizing mechanical leverage to expose the tension points. The torch cuts through the thick steel as if it were butter, but the real challenge is managing the molten slag and the rapid heat transfer. By breaking the chain down into individual segments, the raw material is prepped for the forge. The rust is left behind in the dirt. Only the dense, high-carbon steel core remains. After the heavy shackle is finally severed, the rough stock moves indoors. The transition from chaotic scrapyard to organized production line is immediate. These heavy steel blanks are now categorized by weight and dimension, stacked precisely against the brick wall. They await the immense thermal and mechanical forces that will completely realign their crystalline structure. Inside the induction furnace, the salvaged iron is pushed to its absolute thermal limit. The metal must reach an orange heat, roughly 1,200 degrees Celsius, before it can be forged. At this temperature, the steel's internal lattice expands, making the rigid iron entirely malleable. The operators extract the glowing billet and rush it to the pneumatic power hammer. Heat dissipates rapidly in the open air, so the forging window is aggressively short. The massive hammer strikes with hundreds of tons of compressive force. This is not just about changing the shape, it is about mechanical refinement. Repeated heavy impacts compress the metallic grain structure, forcing the molecules closer together. Forging physically closes microscopic voids left by the casting process or the years of ocean wear. Every strike drives out impurities as flying scale, while the dense core is elongated. The technicians must continuously rotate the stock under the die. If the metal cools too much, striking it will cause stress fractures deep within the shaft. Keeping the bar perfectly horizontal ensures the compressive force is distributed evenly. The raw link is now a solid, uniform cylinder. secondary heating cycle brings the forged rod back to a critical working temperature. This time, the target is the flange. The vertical orientation under the power hammer drastically changes the forging dynamics. Instead of elongating the shaft, the heavy die compresses the metal onto itself, upsetting the end to form a wide, flat disc. This step requires immense control. The operators use long tongs to counteract the vibration and lateral slip generated by the hammer's impact. The steel is flattened outward, increasing the surface area while maintaining a continuous grain flow. This unbroken structural grain is what gives a forged axle its superior shear strength. A machined flange would snap under heavy load. A forged one bends. The shaped axle blanks are left to air-cool on the workshop floor. This slow thermal descent normalizes the steel, relieving internal stresses built up during the violent forging process. Once normalized, the axles enter the machining phase. The flange must be perfectly perpendicular to the shaft, requiring heavy material removal on the lathe. The carbide cutting tool bites into the spinning flange, peeling away the oxidized outer skin to reveal the bright structural steel beneath. The lathe runs at high rotational speed, generating long, continuous ribbons of swarth. This continuous chip formation is a key indicator of the metal's excellent ductility. After facing the outer edge, the spindle is centered for drilling. A precision bit bores directly into the axis of rotation. This center hole is not just a mounting point. It serves as a critical alignment register for all subsequent machining steps. Without a perfectly true center, any minor wobble would be amplified during high-speed operation. The blank is now geometrically true. Over on the long bed lathe, the main shaft undergoes intense turning. The chuck grips the heavy blank while the tailstock supports the far end, completely neutralizing any flex. The cutting tool travels longitudinally down the shaft, removing millimeters of steel with every pass. Friction generates tremendous heat, sending a plume of smoke off the cutting point. The blue color of the metal shavings indicates that the heat is being carried away by the waste material, protecting the integrity of the axle itself. At this station, 1/10 of a millimeter is the difference between a functional part and scrap. The tool bit slowly erases the rough forged texture, leaving behind a mirrored, perfectly cylindrical surface. This exacting dimensional accuracy ensures the axle will eventually spin freely inside the differential housing. The machining continues with the cutting of specific retention grooves. The lathe tool carves a sharp, defined channel into the spinning shaft. This recessed lip will eventually house protective oil seals or locking rings. The geometry of the groove must be absolute. A burr or uneven edge here would cause catastrophic fluid leaks in the final assembly. As the operator retracts the carriage, the finished profile is finally visible. The transition from heavy forging to high-precision machining is fully realized. The completed shafts are carefully stacked, their wide circular flanges resting flush against the workshop wall. What entered this room as a rough, blackened rod is now a polished, dimensionally perfect mechanical component, awaiting its final mounting features. To secure the axle to the wheel hub, the mounting flange requires precise bolt holes. The steel plate is locked onto the heavy drill press table. The operator tightens the securing bolts to prevent the immense rotational torque of the drill from spinning the workpiece. The high-speed drill bit plunges through the dense carbon steel, generating significant friction and smoke. The pressure must be steady to cut a clean, straight channel without snapping the bit. After the holes are bored, the exit wounds on the metal leave sharp, dangerous burrs. A manual scrub with heavy-duty steel wool removes these imperfections. A completely flat mating surface is non-negotiable. Any raised burr would prevent the wheel hub from seating completely flush against the axle flange. The most critical geometry is applied at the gear cutting station. A specialized milling cutter slowly carves deep splines into the top of the steel shaft. These interlocking teeth are what will eventually mate with the transmission's differential gears, transferring massive engine torque directly to the wheels. The cutter indexes around the shaft, making repeated passes to ensure the spacing and depth is mathematically perfect. If the pitch is off by even a fraction of a degree, the axle will shred the internal gearing. A final rotary polishing tool is applied directly against the freshly cut teeth. This secondary abrasive action eliminates microfractures and polishes the spline surfaces to a mirror finish, ensuring a smooth, low-friction engagement within the drivetrain. The machined axle is geometrically perfect, but the raw steel is too soft to survive under a heavy truck. The final step is aggressive heat treatment. The splined end is lowered into an induction coil, rapidly elevating the steel back to a glowing red critical temperature. This extreme heat forces the carbon atoms to dissolve evenly throughout the iron matrix. Immediately, the glowing metal is plunged into a cold water bath. This violent thermal shock freezes the carbon atoms in place, creating an incredibly hard, wear-resistant outer shell. The inner core remains ductile, allowing the axle to absorb shock without snapping. A final intense water spray rapidly extracts the remaining heat from the forged flange, arresting the metallurgical transformation. As the red glow fades to a dull industrial gray, the steel reaches its final hardened state. The finished components are lifted from the cooling basin, the residual water dripping from the freshly cut splines. From loose, rusted scrap metal to a row of precision automotive components, every station added one irreversible step. The extreme heat of the forge provided the strength, while the precise calibration of the lathes delivered the geometry. These axles will soon bear the immense weight and torque of heavy transport. The product is the sum of 100 small precisions. Tomorrow, the line does it all again.